All right, so this week we're going to start talking about surveys and survey sampling. And you can see here, we're in the midst of a presidential election now, and between being called to be surveyed and between the advertisements on TV about what's happening with all the polls, we're surrounded by surveys. In the political realm, they call them polls. And that's what we're going to be looking at today. So, for example, if we look at the previous polls, here's what happened with the last polls taken before the 1996 election. This is the presidential election when President Clinton was running against Senator Dole and Perot was the third candidate. And you can see that, take a look at the bottom line, 96 million people voted in the actual election. So 96 million voted, and Clinton got 49.3% of the vote, Dole got 40.7% of the vote, and Perot got 10% of the vote. Now, here we have listed all these polls. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 of the more popular polls in the US. And take a look at this. The final for Clinton was 49.3, and this one said 51, 51, 53, 49, 52, 44, 49. Pretty good. Pretty good. Similarly for Dole, pretty good. But the fascinating thing is this. Take a look at the Harris poll. The Harris poll was based on asking 1,339 people to give us their opinion of how they would vote. Now, this is 1,339 people versus 96 million. How can 1,339 people predict what 96 million people are going to do? And the same with the others. 703 here, 51% of them compared to the 49.3 of the 96 million. 1,519, 53% of them. 1020, 49% of them, and so on. All roughly, these are all roughly about 1,000, 1,200, 1,400, that kind of order of magnitude, telling us, just by looking at those people, telling us how 96 million people were going to vote. This is the magic. How can this be? You know, and was this just in 1996? And the answer is no. Here's the year 2000. Here again it was 96 million, and this was the year, we don't know what the results really were, but there it says actuals were 48% and 48%. It was a virtual tie, and once again, on the basis of roughly 1,000, well, here's one that's a little bit bigger, 2,000, but on the basis of 1,000, 2,000 people, whatever, look at this. Look at the predictions here. The result was 48%, and they were predicting 47, 45. Pretty good. Same with the 2004. The actual was 50%. And this was also, I haven't put the numbers here, but this was also based on about samples of size 1,000, what the samples of size 1,000 would say. And look at these and compare those to what the actual happened. Look at Kerry, 47, 48, 49, actual 48.3. When we get to the last one we had, prior to the one we're going to have shortly, we see that the final was 52.7% for Obama, and here are the predicted values. They're all very close. And McCain, 46% for McCain, and here are the actual McCain predictions. The average here was 52 of those numbers. Average is 52 versus actual of 52.7. So it's pretty good. Average is 44 versus the overall of 46. So it's pretty good, especially when you look at the sample sizes. The sample sizes here are about same thing, roughly 1,000 or so. So it's amazing. It's amazing how does this all work. And that is the magic that we're going to be looking into today. Now, on a more serious note, the National Center for Health Statistics has, their initial aim was to carry out the vital statistics program, how many people are born, birth certificates, death certificates, and so on. But they've also taken on, in the last 50 years, health surveys. And they've been carrying out these health surveys. Go visit them. It's a wonderful, you see they are now part of the CDC, the Centers for Disease Control. But go visit them and you can see some of these health surveys that they carry out. They started out early 60s with the National Health Examination Survey. Then they carried that out again in the mid-60s and so on. And then they expanded that to the NHANES, so-called NHANES. And there's NHANES 1, 2, 3, and then there was the HHANES for Hispanics. They expanded to that, and so on and so forth. They got a whole bunch of surveys. So it's a very important tool in health area to look at surveys. Another very important source of surveys, and this is much more global. This is from USAID. Go visit them, and there's the. It's funded by USAID. Go visit them and you can take a look at the demographic and health surveys, the DHS. Lauren will be talking about this a little bit in this week, and she'll give you a little bit more depth about these. But the point is that these are a very important component of the information we have on the health of the world. With these, there are two issues. I mean, it's nice to do a survey, but why should we believe it? And the two issues that we are concerned with today are accuracy and precision. How accurate is your survey and how precise is it? So accuracy is a measure of how close to reality the measure represents. So another way of looking at that is the negative of it, and that is the bias. So for example, if we only survey men, then it's not really telling us about the population, it's telling us about half the population. Okay, so it's biased in that respect. Okay, now does the bias matter? Maybe it does, maybe it doesn't, but that depends on the context. But that's what we mean by accuracy. So is everybody properly represented in the survey? That depends that will govern the bias, for example. The precision is how confident are we in the reproducibility of the results. And here depends very much on the population we're looking at. How variable is this population? If everybody in the population is equal to each other, then we need a sample of size 1, and it's very precise. Okay, so the precision depends upon the variability. And this is what we've been sort of working on throughout the course up to now, is worrying about variability. Saying we can do much better when the standard deviation is smaller, or the standard error is smaller. Remember, we said the bigger your sample, the smaller your standard error. This is the same argument here as that. Okay, so accuracy and precision. Now, precision is a function of the sample size and the way that sample was selected. This is important too. We'll see that in a minute because when we look at some of these designs that go along with these surveys. So some designs actually yield more precision than others. And I'll expand on that as we go along. So, remember this slide? We said we have a population, and from that population we're going to take a sample, and then on the basis of that sample we're going to make inference about the population. So this is the way we introduced inference. And let's return to that, because that's exactly what we're doing today. We are going to be looking at the sample. Up to now, we said, oh, we've just got a simple random sample. But let's look at the sample a little bit more closely, and that's what we're going to do today. Now, What we say we wanted from the sample, we said that the sample must be representative. That's an idealization. We never know whether it's representative or not. Okay, so what we resort to is a random sample. Okay, we go back to thinking about a random sample. What property about randomness are we going to be using? So far, we've been using this assumption that basically we haven't said anything about the population. We've said the population is infinite and we're going to take a simple random sample from that population. So, for example, getting a little bit of notation, if we're going to take a sample of size little n from a population of size cap n that has mean mu and standard deviation sigma. So now, I haven't mentioned this cap n before. We've never mentioned this cap n. If at any time we said it, we probably said, oh, it's infinite. I mean, that's the infinite population model that we've been working with. All right? But let's look at this. Does it make any difference? Does this population size make any difference? If it's small, yes, it can. Right? What's important is this sampling fraction. So if we're going to take a sample of size little n from a population that's big N, and we take a simple random sample, what do we mean by simple random sample? We now have the notation to tell us what we mean by simple random sample. It means that every person in the population has the same probability of being in the sample, and that's the probability. So if we're going to sample 10, well, let's say we're going to sample 100 and our population is 1,000, then F is equal to 100 over 1,000, that's 1 over 10. So everybody's got a chance of 1/10 of being in the sample. Now, we're going to be talking a little bit more about this later when we start talking about sample weights, because this might not be true everywhere. But okay, so think about, even if you have a finite population, think about we're going to take a sample, and once we've taken the sample, that's it. We don't go back and take it again. It's not a candidate to be taken again. That's called no duplication. Okay, so we just take one. So it's called sampling without replacement. Now, there's our sampling fraction. That's what that's called. F is called the sampling fraction. Now, the central limit theorem still holds with this. The only difference is that the standard deviation of x bar, namely the standard error, is actually this. Now, we recognize sigma over the square root of n. That's what we had before. But now we've got what is called the finite correction factor. Finite population correction factor. That's this thing. The square root of, let me make it clearer. So it's the square root of 1 minus f is called the finite population correction factor. Now, if we can assume that f is approximately 0, then we're back to our old sigma over square root of n, and there's nothing new. When is f approximately 0? Well, remember, f was the sample size over the population size. That was f. So if we've got a huge population, 300 million in the US, and we're going to choose a sample of 1,000 people to ask them about how they're going to vote, that's 1,000 over a million, so f is 1 over 1,000, so it's trivial. 1 minus f, and the square root of that is going to be very, very close to 1, and so it doesn't make a difference. But the important thing to notice, the interesting thing to notice, is that n is what's important. Look at the standard error. The standard error is n. It's not f, because f is going to be approximately 0. So f doesn't matter. In particular, the population size doesn't matter. So n doesn't enter into the discussion, except through f, of course. But if f is close to 0, it doesn't matter. So this is something that's counterintuitive. People don't believe this at first, that if I'm going to take a sample of size 1,000, it doesn't matter if I take this 1,000 from the city of New York with 10 million, let's say, or if I take that 1,000 from the US, which is 300 million, or if I take that 1,000 from the world, which is 7 billion. It doesn't matter. As long as it's a simple random sample. Now be careful, that's a very loaded word. But as long as everybody has the same chance of being in that sample, then whether I'm sampling from New York City, whether I'm sampling from US, or whether I'm sampling from the world, it doesn't matter. The standard error, there it is, the standard error is only a function of how big the sample size is, n, assuming sigma is the same everywhere. All right? So under those two assumptions, basically, one, that f is approximately 0 and sigma is constant, which sometimes is stretching things a little bit, but it's purely the sample size that matters. Counterintuitive, but go to bed tonight thinking about it, and I'm sure you'll wake up in the morning and you'll say, oh, right, he was right.